A linear search, also called sequential search, is defined on a finite sequence, an array, list, or any ordered collection, a sub-0 to a sub-n-1 of elements drawn from a universe U and a target value x in U. The problem is to determine whether there exists an index I such that a sub-I equals x, and if so, return the smallest such I, the first occurrence. If x does not appear, the algorithm must report not found. Formally, we seek I equals the minimum of j in the set 0 to n-1 such that a sub-j equals x if the set is non-empty, otherwise I equals -1. Think of walking down a row of lockers and opening each one until you find the key you need. You stop as soon as you succeed or reach the last locker. Linear search open parenthesis a 0 to n-1 close parenthesis, comma x close parenthesis colon. For I gets 0 to n-1 do. If ai equals x, then return I first position where x appears. Return -1 x not present. Step-by-step explanation. 1. Initialize the loop index I at 0, the first element. 2. Compare I with x. 3. If they are equal, the search succeeds, return I immediately. 4. If not equal, increment I and repeat step 2. 5. When I reaches n, all elements have been examined, return -1 to indicate failure. Explanation. We prove that the algorithm always returns the correct answer using mathematical induction on the length n of the array. Base case n equals 1, the loop runs for I equals 0 only. If a sub-0 equals x, the algorithm returns 0, which is the smallest index satisfying the condition. If a sub-0 not equal x, the loop finishes and returns -1, correctly indicating that x is absent. Inductive hypothesis. Assume that for any array of length k, where k is at least 1 and less than n, the algorithm returns the smallest index I where a sub-I equals x, or -1 if x is not present. Inductive step array length n, the algorithm first checks a sub-0. If a sub-0 equals x, it returns 0, which is trivially the smallest index. If a sub-0 not equal x, the algorithm proceeds to search the suffix a sub-1 to n-1, length n-1. By the inductive hypothesis, the recursive call or the continuation of the loop returns the smallest index j in that suffix where a sub-j equals x, or -1 if none exists. The returned index for the whole array is then j plus 1, because the suffix starts at position 1, which is exactly the smallest index in the original array. Thus, the algorithm is correct for length n. By induction, the algorithm is correct for all n greater than or equal to 1. Explanation, let n be the number of elements. Best case, the target appears at the first position. Only one comparison is performed. Hence, t best of n equals 1 equals theta of 1. Worst case, the target is absent or at the last position, so every element is examined. The number of comparisons is n, hence t worst of n equals theta of n. Average case, assuming each element is equally likely to be the target, and the search stops at the first occurrence. The expected number of examined elements is the average of the positions 1 to n. E of t sub avg of n equals 1 over n times the sum from I equals 1 to n of I equals 1 over n times n left parenthesis. N plus 1 right parenthesis over 2 equals open parenthesis. N plus 1 close parenthesis over 2 equals theta of n. Thus, on average, we look at about half the list. These formulas can be written using summations to show the derivation explicitly. Worst case sum equals the sum from I equals 1 to n of 1 equals n. Average case sum equals 1 over n times the sum from I equals 1 to n of I. The big theta notation captures the asymptotic growth, linear time. In real life, this is like checking each person in a line for a lost wallet. If the wallet is at the front, you finish instantly. If it is at the back or not there, you have to ask everyone. Linear search uses only a constant amount of extra memory, an integer index variable, and a few temporary booleans. No additional array or data structure proportional to n is allocated. Therefore, the auxiliary space is S of n equals theta of 1. Because the algorithm works directly on the input array, it is called an in-place algorithm. This property is valuable on memory-constrained devices, for example embedded sensors, where allocating extra buffers is impossible. Formally, if we denote by m the number of memory cells used beyond the input, Then m equals c for some constant c independent of n, so the space complexity class is constant. The sentinel or guard variant adds one extra copy of the key x at the end of the array, eliminating the need to test the loop bound on each iteration. Step 1. Allocate a new array b of length n plus 1. Step 2. Copy a 0 through n-1 into b0 through n-1 and set bn equal to x, the sentinel. Step 3. Initialize I equals 0 and loop while bi is not equal to x. Do I equal I plus 1. Step 4. After the loop, if I is less than n, return I, else return -1. Why is it faster? The loop body now contains only the comparison bi not equal to x. The boundary check, I less than n, is removed from each iteration, saving one conditional branch. The total number of comparisons becomes exactly n in the worst case, instead of n plus 1 and 1 in the best case, but the constant factor is lower because the processor performs fewer instructions per iteration. In practice, the gain is modest for small n, but noticeable for very large arrays or tight inner loops, for example searching in a low-level device driver. Mathematically, the Sentinel version performs t-sentinel of n equal I found plus 1 comparisons, where I found is the index of the first occurrence. The ordinary version performs I found plus 1 comparisons plus an extra bound check, that is I found plus 2. So the improvement is exactly 1 comparison per iteration. Linear search data may be unsorted, no extra structure required. Best case theta of 1 key at first position, average case theta of n approximately n over 2 comparisons. Worst case theta of n comparisons, typical space theta of 1. Binary search, input must be sorted or stored in a structure that allows order. Best case theta of 1 key at middle after first split. Average case theta of log n approximately log base 2n. Worst case theta of log n, ceiling of log base 2n comparisons. Typical space theta of 1 usually works in place. Hashing direct address or hash table, a hash function that maps keys uniformly, table size greater than or equal to n or handled collisions. Best case theta of 1 ideal constant time probe, average case theta of 1 expected constant. Worst case theta of 1 average or theta of n in worst case clustering. Typical space theta of n for storing the table. Key differences, order requirement, linear search works on any order. Binary search needs sorted order. Hashing does not need order but needs a hash function and extra storage. Complexity trade-off, linear search is simple but linear time. Binary search reduces time to logarithmic at the cost of sorting or maintaining a sorted structure. Hashing gives expected constant time but requires extra memory and careful handling of collisions. Use case analogy. Finding a name in an unsorted phone book leads to linear search. Finding a name in an alphabetically ordered directory leads to binary search. Finding a record by ID in a database with an index leads to hashing. Thus, when data is small or unsorted, linear search is acceptable. For large, sorted collections, binary search dominates. For fast lookups with many queries and tolerable extra space, hashing is preferred. Explanation: typical exam items related to linear search include 1. Write pseudocode. Students must produce a clear loop that scans the array and returns the index or -1. The answer should mirror the pseudocode given earlier, explicitly showing initialization, the comparison, and the return statements. 2. Compute number of comparisons. Given an array of size n and a target that is known to be at position k0 based, the student calculates that the algorithm performs k plus 1 comparisons. For worst case absent or last element, the answer is n comparisons. 3. Prove complexity. Students are asked to justify that the average case running time is open parenthesis, n plus 1 close parenthesis divided by 2 by summing the series sigma from I equals 1 to n of I divided by n. They may also be required to state theta notation for best, average, and worst cases. 4. Sentinel variant. Write the Sentinel version and argue that it saves one bound check per iteration, leading to at most n comparisons rather than n plus 1. 5. Compare with binary search. Explain why binary search cannot be used on an unsorted list and give the respective theta values. When answering, students should use clear variable names, comment the return values, and show the summation steps for the average case proof. Example answer snippet for part 2. Given n equals 10 and target at index k equals 3, Comparisons equals k plus 1 equals 4. Even though linear search is simple, it has several practical limitations. Unsorted data. The algorithm does not exploit any ordering, so it cannot be faster than scanning every element. If the data can be sorted once and many searches are performed, a binary search becomes more efficient. Duplicate elements. The basic version returns the first occurrence. If the problem requires the last occurrence or all positions, the algorithm must continue scanning after the first match, increasing the number of comparisons. Large datasets. For very large n, millions or billions, the linear scan becomes costly in time and may cause cache misses because each element is accessed sequentially. In such cases, indexing structures, B-trees, hash tables are preferred. External memory. When the list resides on disk, each element read may involve a costly input-output operation. Linear search would trigger big O of NIOs, overwhelming the system. Blockwise reads or indexing mitigate this. Parallelism. Linear search is inherently sequential. While you can partition the array and search in parallel, the overhead often outweighs the benefit unless the array is massive and the platform supports many cores. Real-world analogy. Looking for a specific spice in an unordered pantry by opening every jar until you find it is fine for a few jars. But if the pantry holds thousands of containers, you would reorganize them alphabetically, enable binary search, or label each jar with a QR code that maps directly to its contents hashing.